Okay, so this lesson is the last section of Chapter 8 that we're covering, and it's going to be on some basic matrix algebra. So we're not really going to be doing any applications of adding, subtracting, or multiplying matrices. However, those are common. They're questions that could come up on certain standardized tests. So we're going to go through some definitions first and some properties of matrices. So equality of matrices. Two matrices are basically equal if and only if both the following are true. A and B have the same dimensions, and every pair of corresponding entries is equal. So one type of question or problem you might see is, like, let's say that I have matrix 1, 2, 3, 4. And that's going to be equal to the matrix, like, x minus 3. This is just a really simple example. And you need to solve for x. Well, we know that because these matrices are equal to each other, the x minus 3 is going to have to be equal to 1. Therefore, x must be equal to positive 4. So in order to be able to add two matrices or subtract them, the matrices have to have the same dimensions, because it's really easy. You're just going to be adding or subtracting the corresponding elements to the matrices. So for example, if we want to add matrix A and matrix B, so find the matrix that would result from adding these two matrices. We're just going to be adding the corresponding terms. So negative 4 plus 2, 0 plus 3, 1 plus negative 4, and 2 plus 0. Okay, so that's the matrix that we get from adding the two matrices. Okay, notice that A is a 2 by 2 matrix, B is also a 2 by 2 matrix, and the resulting matrix is also a 2 by 2 matrix. To subtract, okay, so if we want to find the matrix that results from subtracting matrix B from matrix A, so that's negative 4, 0, 1, 2, minus okay, so I'll do negative 4 minus 2, which is negative 6, 0 minus 3, 1 minus negative 4, which will be 5, and then 2 minus 0 is 2. So you can only, it's important to remember, you can only add or subtract matrices if they have the same dimensions. Okay, now a zero matrix is a matrix where all entries are equal to 0. So for example, if I have some matrix A, which will be 1, 2, 3, 4, and I were to add a zero matrix to that matrix, I would just end up with matrix A. Okay, so the zero matrix is the additive identity for an n by n matrix. So like the point here is that, like real numbers have different properties, but matrices also have properties that are similar to real numbers. Okay, so for any matrix A, there exists an additive inverse, negative A, such that each entry of negative A is negative of the corresponding A. So for example, if we were to add A and negative A, so negative A would just be matrix A, but where each element is the opposite sign, okay, we would end up with a zero matrix. Okay, so these are just some properties of matrix addition. So like the real numbers, matrix addition has a commutative property of addition, associative property of addition, and then additive identity property and additive inverse property. Okay, so if you want to multiply a matrix by a scalar, you just need to multiply each element of the matrix by that scalar. So for example, if we want to multiply, I don't know, let's do 3, 7, negative 2, 4, okay, by 3, we're just multiplying each element, so we'd have 9, 21, negative 6, and 12. Kind of like scalar multiplication for vectors. Okay, so if we want to find the matrix that results from multiplying matrix A by negative 5 and then adding matrix B multiplied by 2, I can first multiply matrix A by negative 5, so that'll be 5, negative 10, 15, negative 20, and then add matrix B multiplied by 2. And now, because these are two 2 by 2 matrices, I can just add the corresponding elements. To get my final matrix. All right, matrix multiplication is a little bit more complicated. And to multiply two matrices, we use the row by column method. Now, this is the important part. So for the product AB to exist, the number of columns in the first matrix A must be equal to the number of rows in the second matrix B. So if we wanted to multiply matrix A times matrix B, and let's say that matrix A had dimensions m by n, then matrix B would have to be would also have to have n rows, and then by some other number. Okay, and this will make sense. So basically, the number of columns in matrix A has to match the number of rows in matrix B to be able to multiply the two matrices. So you can't multiply just any two matrices. So those need to be equal. Now, the matrix that results from multiplying these two matrices would be dimensions m by p. So first we're going to look at, we have these 4 different matrices, and we're going to determine whether or not these products exist. So if we were trying to multiply matrix D by matrix A, okay, matrix D is a 1 by 2, and matrix A is a 2 by 3. So because the number of columns here matches the number of rows here, this product will exist. And the dimensions of the matrix that you get from multiplying these two matrices would be 1 by 3. Okay, so, let's go down here. Okay, so if we try and multiply matrix C by matrix B, okay, matrix C is a 2 by 2, and matrix B is a 3 by 2. So because the number of columns in matrix C does not match the number of rows in matrix B, this product actually doesn't exist. And then to try see if B times A exists. Okay, matrix B is 3 by 2. Matrix A is 2 by 3. Okay, so because number of columns matches the number of rows, this product will exist, and the matrix B times A is going to be a 3 by 3 matrix. Okay, so matrix multiplication is a little trickier than matrix addition or subtraction. And I already mentioned that we're going to be using the row by column method. And I think that this will make more sense once we actually go through an example. So matrix A is a 2 by 2 matrix, and so is matrix B. Okay, so number of rows, so when we try and find A times B, the number of rows of A matches the number, the number of columns for A matches the number of rows for B. Therefore, we know that we will end up with a product. Okay, and the matrix that we'll get from multiplying A times B will also be a 2 by 2. Okay, so row by column. So I'm going to use row 1, column 1, to find the first element of the matrix here. So we'll have 1 times 5 plus 2 times 7. Okay, that's going to be the first element. Then I'm going to move over to column 2 to find the next element. So 1 times 6 plus 2 times 8. Okay. So now this first row has hit both of the columns. Oops. So I'm going to move down to row 2 in column 1. Okay, so we'll have 3 times 5 plus 4 times 7. And then column 2 to get 3 times 6 plus 4 times 8. So now we have our 2 by 2 matrix. And we can simplify each element. So we'll get 19, what is that, 22. It's 15 plus 28. 43 and 50. Okay, so let's find B times A and see if that's the same as A times B. Okay, so B times A is also going to be a 2 by 2 matrix. It won't always happen that A times B is the same dimensions as B times A. It's just because we're multiplying two square matrices. And just because A times B exists does not mean that B times A exists. It's totally dependent on the dimensions of each matrix. Okay, so we'll have another 2 by 2. So I'm going to go row 1 by column 1. So it'll be 5 times 1 plus 6 times 3. Then I move over to column 2. And 5 times 2 plus 6 times 4. Okay, now that I've hit both columns there, I move down to row 2, column 1. 7 times 1 plus 8 times 3. Okay, and then row 2 by column 2. 7 times 2 plus 8 times 4. Okay, so 23, 34, 24 plus 7, 31, and then 14 plus 32, 46. Okay, so we can see that A times B is not equal to B times A. We end up with two different matrices. So there's no commutative property of matrix multiplication. Okay, so let's find A times B here, if it exists. Okay, so A is a 2 by 3 and B is a 3 by 2. Okay, so because number of columns here matches the number of rows here, the AB, the matrix AB, will end up being a 2 by 2. Oops. Okay, so we'll start going row 1 by column 1. So the first element will be 1 times 0 plus 0 times 1 plus 2 times 0. Then move over to column 2. And we'll have 1 times negative 1 plus 0 times 2 plus 2 times negative 2. Okay. Then row 2, column 1, negative 3 times 0 plus negative 1 times 1 plus 4 times 0. And row 2 by column 2, negative 3 times negative 1 plus negative 1 times 2 plus 4 times negative 2. 0, negative 5, negative 1, 1, negative 7. Okay, and then let's look at finding B times A. So B times A. Okay, so this is 3 by 2 and 2 by 3. columns matches the rows, and this will result in a 3 by 3. Okay, so we'll go row 1 by column 1. Then row 1 by column 2. And then finally, let me get myself a little more room. Row 1 by column 3. Okay, moving down to row 2 and then column 1. Row 2 by column 2. Row 2 by column 3. Okay, and then row 3 by column 1. Row 3 by column 2. And row 3 by column 3. Okay, so then simplifying each element, 3, 1, -4, -5, -2, 10, 6, 2, -4. Okay, and again, let's find A times B if possible. This is a column matrix times a row matrix. So this is 3 by 1, 1 by 2, because the number of columns matches the number of rows. This product will result in a 3 by 2 matrix. So it'll be row 1 by column, row 1 by column 1. Okay, and then row 1 by column 2. Row 2 by column 2. Row 2 by column 1, and then row 2 by column 2. My bracket's not big enough. And row 3, column 1. And row 3, column 3. Okay, let's see about finding B times A. Oops. One by 2 times a 3 by 1. that product will not exist. Okay, so here are some of the properties of matrix multiplication. So there's the associative property of multiplication, and then also the distributive property of multiplication. Or, sorry, the distributive property. Okay, so the only piece of information from section 8.5 that I want to pass along to you guys is on determinants. And what a determinant is, and the reason I want to show you guys how to find a determinant is because I have seen it as a standardized test question, so I want you to have heard of it. Matrices is something that you will study more in depth in linear algebra, so we are very, very surface level right now. We're not looking at applications. There is another method for solving linear systems called Cramer's rule that uses determinants, but we already have enough methods right now for being able to solve linear systems. So I'm just going to show you guys briefly how to find a determinant. Okay, so every square matrix has a number associated with it called its determinant, and it's denoted as det A, or looks like the absolute value of A or the magnitude of A, but it's not a magnitude. Determinants can be negative, so unlike when we've used the absolute value bars to represent magnitudes of like vectors or complex numbers, the determinant can be a negative value. Okay, so I'm going to show you guys how to find the determinant for a 2x2 matrix. So 2 rows, 2 columns. So here is the notation for determinant. Okay, so it means the same thing as this. It's just you can see the elements of matrix A in that second notation. And to find the determinant, you're going to do A times D minus B times C. So the product of the first diagonal minus the product of the second diagonal. Okay, so if we want to find the determinant, I'm going to name this matrix A. So if we want to find the determinant for A, it's going to be for product of the first diagonal minus product of the second diagonal. So -4 plus 3, so -1. Okay, and I'm going to call this matrix B. So if I want to find the determinant for B, it'll be the first diagonal minus the product of the second diagonal. So that'll be 15 minus 4, which is 11. Now, for finding the determinant for any larger n by n matrix, you probably want to use your calculator. So you can input the matrix into your calculator. You guys already know how to do that. And then you want to call up the matrix menu and then use the arrow key to go over to the math menu. The same list where you guys found RREF, reduced row echelon form. I think determinant's number 1. So you want to hit enter to call up that operation, and then you need to go back to the matrix menu to call up matrix A and hit enter. And that will give you the determinant of any n by n matrix, a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5, and so on.